In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed.
To go live, so just I don't know how much of this talk we want on the air.
All right, hello and welcome. We're here for episode 57 or 58 of I almost said Flat Earth Fridays of Aether Cosmology, Aether Roundtable. Tonight we're going to be talking about Sagnac in 1913, continuing the history of interferometry. So we're going to get into that. So what we're looking at here is a top-down view of Sagnac's interferometer. And we're gonna go through, why he designed this, what it measured, what the implications are, and how that affects the current mainstream paradigm. So in 1913, some French guy spun his interferometer around and found that he measured the speed of light as c plus or minus v, going with or against the rotation of the apparatus. Why is this important? Why does it matter? Who cares? Well, the answer to that is that it's one of the most significant experiments with light that's ever been done, and it found that you could measure absolute rotation. Now, when you get into further experiments that were done, it turns out that you could measure linear motion. And this is extremely important because in 1905, a very special theory was put forward that explicitly is built upon the idea that you can't measure linear motion. And this idea was put forward to keep the heliocentric cosmology alive. So this experiment is very important, and especially its configuration. So we're going to get into all the specifics on that. And this device, this measurement, this application is used in inertial navigation systems, GPS, all kinds of different things. And it's one of the most precise measurements that can be made using light. So to start off with the history again, and I kind of want to start off by always steel-manning relativity, and so we can know why these measurements falsify the theory that was put forward to give and why that theory doesn't have explanatory power over the measurements. So a quick recap from our boy Einstein. He says that the first postulate of his theory is that all inertial frames are equally valid, and he defines an inertial frame as any frame that's in uniform rectilinear motion. And then he goes on to say that the second postulate will be that the speed of light is constant, and that's irrespective of the motion of the observer or the source. And with that, he adds that there is no need for a physical medium for light to propagate in. So there's no absolute reference frame. And with that, he also removes the mathematical notion of a absolute reference frame and says that all motion is relative. So when you analyze time and space, those two coordinates will be, with respect to some other moving system. And it's important to note here that later on in this paper, he explains that his equations apply in a uniformly rotating system, any closed polygonal line, and any continuously curved line, which is otherwise known as a circle. His equations apply. So he's defining that as an inertial frame. So if we take a look here at this light source here, and we have the photographic recorder here, his theory predicts that there's no relative motion between these two, and that they're both in inertial frames because they're both moving at a constant uniform velocity, and you can't tell. Now, although you can treat a rotation as an acceleration, etc., right? This is a specific point on uniform rotation. So, he says it's equally valid. And later in his theory, in his 1915 theory, the general theory, he doesn't say that this no longer applies and you have to use general relativity explicitly, but we'll get into that as we continue on. But just to fully note that his equations are supposed to apply in a uniformly rotating scenario. And this is also noted by Thomas precession, where they explain the anomalous orbital behavior of an electron around a nucleus via Thomas precession, which is adding link contraction and time dilation to the orbit of the electron through taking infinitesimal sections of that orbit and making them 90 degrees to one another, and then doing a transformation to facilitate link contraction and time dilation. So it's already canonized that they apply in a circle. So the modern refutation to Sagnac will say that special relativity doesn't apply to rotation, but clearly we're looking at, the works of Einstein where it explicitly says it does. Fix that real quick. All right, cool. So this is another overview of the apparatus here. We got our light source. We've got half silvered mirrors that split the beam. And then we have mirrors that reflect it so that the beam can go clockwise and counterclockwise with respect to the rotation of the apparatus as it rotates. And then they will complete their circuit, and then they will recombine at the A beam splitter, where they will hit a photographic plate, and they will either be in phase or out of phase. So that's the idea of how this apparatus works. And they'll be out of phase proportional exactly to the velocity of the rotation of that angular velocity. All right. So to kind of recap with the special theory of relativity saying that there's no absolute reference frame to measure velocity. This, of course, was a result of the Michelson-Morley measurements. So if you were to take a fixed point in space, so kind of think about it like this, if you were to, where this white X is right here, if you were to mark that off and say, we're going to have this as our fixed point of reference, and then this Earth is going to move around the sun, you would be able to preserve that distance as from that position of absolute space to measure velocity to. Now, the special theory says you can't do that. What you would have to do is take the position between the Earth and the sun and not account for any additional movement with respect to a fixed point of origin. And from there, they introduce link contraction and time dilation, which makes it so that you're actually unable to measure it because you're traveling at relativistic speeds, which means that you're not going to be able to measure a difference in the speed of light in your reference frame. You would have to do a transformation to the sun, and then you could see from that perspective, stationary on the sun, that the Earth in motion is measuring a different speed of light. So that's it sounds all confusing and whatnot, but that's what they had to put forward to keep the idea that the Earth is in motion around the sun after they made that measurement. So when you get into an orbit around the sun, right, obviously that's a circle or some sort of an ellipse, depending on one second. Depending on what paradigm you believe in. So what Einstein had to basically say was that this orbit's so big that you can treat it as linear, you can treat it as a straight line, and that's why it doesn't work. And that's why there's no absolute space. But obviously that's pretty ridiculous, because either way they would still be, on an orbital path of an ellipse and or a circle, right, for the geocentric equivalent. So that's where they have to introduce the general theory to get a little more leadway in there and say, well, it's actually not even traveling in a straight line. We're actually traveling in a curved gravitational well. And it's like, okay, dude, that checks out. And, all this is due to consistent measurements that were done with light that show that you can make measurements with respect to absolute space to measure velocity. And this is what they had to introduce to get you further and further away from that. So this is just introducing that those ideas of link contraction and time dilation are supposed to be physically real, and that you're not supposed to treat them as like apparent effects. And Einstein states here that if you could introduce a stationary observer relative to two coordinate systems that are in motion relative to one another, you could actually measure the link contraction and time dilation from that reference frame. So he's saying that those are actual physical effects, and that they're not to be not to be dismissed as like a philosophical or like, it's just an apparent effect or something like that. These are physically meaningful, supposedly, right? Um, and then another part of importance of this is that when you get into the math for how you derive the prediction for the measurement that's made with a rotating interferometer or a stationary one that has a right angle to it, like the Michelson-Morley one, you can use an equation that's just with respect to absolute space, and that will account for the timing difference going clockwise or counterclockwise. So when you math this out and reduce it down to the change in the phase difference from the start, will be equal to 4 times the area that light has to travel, and then times the angular rotation rate over the wavelength and the frequency, which is just the speed of light. But if you're using a specific frequency, you're gonna have it tuned to that. So you enter all that, and that will tell you how much phase difference there will be after those clockwise and counterclockwise beams connect with one another. And that's a very, very simple derivation. It's very, very elegant, even if I dare say so myself. And then when you get into the postulates that were put forward by relativity theory that we mentioned earlier, the relativistic derivation, if you're not going to allow absolute space or assign velocity vectors for electromagnetic processes, then you make the prediction that the speed of light completes the circuit irrespective of the rotation rate at the same time, and there will be no fringe predicted. So that's the actual prediction for relativity theory, and it makes, it's incorrect. So it's an invalid theory. You're free to disregard it. Now, the important part of this is that it'll be later shown experimentally that this equation for rotation, where it uses the symbol for angular rotation and area for the area of the for the path of light that it would travel over. That's what we were looking at with the Sagnac device when it had the S shape in it. That S is denoting the area that light had to travel inside that interferometer. So what will be shown experimentally is that you can just use length instead of area and velocity instead of angular velocity, and somehow the measurement makes the same exact prediction, and it all works out. So it's really weird. So we'll get into that as we continue. And just to further show, this is Post in 1967 stating that relativity theory, to be consistent with its principles, you have to, it predicts no fringe for a Sagnac interferometer, and especially for the linear variant of it, it predicts no fringe because of the postulates of the constancy of C and how they defined an inertial frame. So if the laws of mechanics hold good in that frame, then the theory predicts that the speed of light will be a constant in that frame. Now, this is such a big issue that since the 1913 publication of Sagnac's experiment, there have been 21 plus. This is noted in 1996 with this is Niklaus and others doing their own Sagnac measurement, and they end up saying that they end up giving 21 citations of different explanations where people are trying to derive the Sagnac effect as a result of relativity theory, and it can't really be done. And when I say it can't really be done, I mean it can't be done. No one's ever done it. And the explanation they were going with for a while was Paul Longeview's explanation, and that was that you have to use the general theory. So we'll touch back on at the end here of a specific falsification of the general theory's explanation for it, showing that neither the special nor the general theory have explanatory power over the Sagnac effect. And the issue that the theory has is that it has to invoke a fictitious frame to try and explain it. So it has to invoke an observer in absolute space to account for the first order timing difference due to the velocity, angular or linear, doesn't matter. Okay. So now that we've kind of caught up on the history of why, if anyone has any questions, this would be a great time to take a little question break or answer any questions like that. All right, cool.
Looks like you're good to go.
Cool. I'm going to hit some water real quick and we'll continue.
We got 20 Sagnac experts in here, it looks like.
Dude, we got 20 Sagnac lads in here, and respect. Respect. All right. Well, if anyone has any questions, you know where to find me. Yeah. All right. So this is the night from, we're going to read a little bit from the 1913 publication. The luminiferous ether is detected as a wind effect relative to the ether using a uniformly rotating interferometer. And if anyone would like an Easter egg on my channel, there may or may not be a rap version of a full reading of this paper by MC Young Sagnac. I'm not going to post a link to it, but you guys can find that. It is available. It's out there. It exists. Shout out to MC Sagnac. So anyway, so there's a specific reason why he chose that geometry for that interferometer, and we're going to get into that now. So as he says, I uniformly rotated at one speed or 2 turns per second at a vertical axis, a horizontal plane on which the various components of the interferometer were firmly anchored, analogous to the one I used in a previous research described in 1910. Interfering beams after reflection from 4 mirrors placed at the edges of the rotating platform were superimposed and traveled in opposite directions around exactly the same horizontal circuit circumscribing the area S. A rotating system also contained the light source, a small electric lamp, and the detector L, a fine-grained photographic plate registered the interference fringes at the focal point of a lens. So that was just describing what we were looking at earlier. Now we'll take another look here at this. Shout out to Manus Stone, who saw that I was doing a little Sagnac presentation and provided some excellent visuals. So we can take a look at what the light path looks like when it's traversing its path here. So we'll take a look at that now. I don't think there's any volume. So anyway, we'll just play it out here. So we're starting as a photon, doing air quotes here, lads. Starting as a photon here, and we're traveling out, and then this is going to split into the clockwise and counterclockwise beams. Here we go.
And yes, those tracks are no audio at all.
Nice. All right, and then we have one more configuration, just a simpler version here with a little rotation. So this will be showing the out of phase difference when the rotation is added to the component. So in the first one, the device was stationary, no rotation. They both hit the photographic plate at the same time. Now we're adding rotation. One gets there a little faster than the other one, and the other one is delayed by the same amount. So this is evidence for absolute space, because otherwise this measurement wouldn't exist. If there was no absolute space, the timing difference preserved for the clockwise and counterclockwise distance change due to the rotation wouldn't be registered. The speed of light would just complete the circuit, and there would be no fringe. So this is a direct refutation to special relativity, and we'll keep continuing on here. We'll take another look at the interferometer. So this is just the same view. This is the area of light. So this would be our A in that equation from earlier, and then the rotational rate would be the omega that we looked at. We got our clockwise and counterclockwise, recombines as it rotates, and then they will be out of phase with respect to the velocity with or against the rotation. And remember, the reference frame is defined as inertial by Einstein. So his theory predicts that there is no way to measure relative motion between 2 inertial observers using light. And yet there's a fringe that exists in the first order, whereas even if you were to generously try to apply his equations, they would predict a much, much smaller fringe shift that you wouldn't even be able to observe, because you would be, the rotating observer and all that, it would be in their frame. So they wouldn't even observe it. All right. So we'll read a little bit on what Sagnac's explanation was for the measurements. So optical rotation effect. Measured from the fringe spacing, the displacement Z from the interference center that I observe with the preceding method is a particular case of the optical rotation that I have defined earlier, and which, in context of the current ideas, should be constructed as a direct observation of the luminiferous ether. Shout out to the luminiferous ether. In a system moving as a whole relative to the ether, the propagating time between any 2 points of the system should change in any way similar to the stationary system subjected to an ether wind. The relative speed at which each point of the system will be the same and directly opposite of the speed at any point in which would contain the waves in a manner similar to an atmospheric wind carrying sound waves. The observation of the optical effect of such a ether wind relative to the, quote, stationary ether is constitute proof of the ether's existence, just as the observation of the wind relative to the atmosphere on the speed of sound in a moving system would constitute, carrying everything else being equal, a proof of the existence of a stationary atmosphere enveloping a system. So what he's saying here is similarly to how globular proponents think that the atmosphere moves in lockstep with the rotating Earth. He's saying, and within that there's winds. He's saying that there's an ether wind that moves in lockstep with the Earth, and within that, motion creates its own optical vortex, and that's what is allowing for that timing difference to be measured, and that this is proof of the ether. And I agree. All right, and this is the equation he used. So earlier, the formalism that we looked at was a little more elegant, but this is when you reduce this down, it's the exact same thing to what we looked at earlier for the equation. And he's just described, and also this equation, like I was saying earlier, is equivalent to the linear variant that Michelson and Morley used to derive the velocity for their measurements with respect to how they were trying to derive the velocity of the Earth around the sun and the predictions for that. So we know that these equations give the correct prediction for velocity in regards to an interferometer. So again, here's what that looks like when you reduce it down. Very nice and elegant. All right, so in conclusion, Sagnac writes here, the observed interference effect is very much the effect of optical rotation due to motion of the system relative to the ether, and directly shows the existence of an ether, a necessary condition for the luminiferous waves proposed by Hudgens and Fresnel. Shout out to the lads who proposed that. All right, so that was Sagnac in 1913. Well, maybe his apparatus was defective or something, and that was just the wrong way to do it or something, right? So we're going to look at an experiment done in 1942. That was a replication of Sagnac, and then they also did a couple other interesting configurations that completely falsify the special and general theory that were put forward to give explanatory power. So before we get into what those lads did, we'll take a look at Einstein here in 1916, I think this is, where he says, or where he's introducing that his general theory will be the theory that's used for rotation frames. But again, he doesn't ever go back on what he said in the special theory papers or anything like that. He just says, now the preferred method is going to be this. And then they would be going forward with Paul Longeview's explanation for how they treat the transformation. So what they do is they invoke a cylindrical coordinate system, and they put a fictitious observer in the center of that coordinate system. And from that observer is watching a non-inertial observer measure the speed of light being different as he's rotating around the rim of the interferometer. So that's the way they look at it. So they need that fictitious frame at the center. They need that non-existent observer, that invocation of absolute space, to preserve that that distance for them, so they could have a timing offset. All right, so let's see. I think we covered everything that needs covered in that. So yeah, we'll get into Dufour and Prunet's experiment here. So they had a light source and a detector fixed to the lab wall, and they had a beam splitter here that was angled off that would split the beams to two 45-degree angled mirrors that would hit two other 45-degree angled mirrors that would then hit some vertical mirrors that would have the light go across the circuit on a rotating platform, and then on the end of its circuit, it would hit the same 45-degree angled mirrors, and it would go back to the top platform, which is stationary, and then those 45-degree angled mirrors would send it back to the original beam splitter, which would send it back to the detector, which was fixed to the lab wall. So remember back how Einstein defined an inertial frame as being in uniform rectilinear motion at a constant velocity, and also any rotation in any uniform rotation, right? But then he was like, well, maybe not for that one. Maybe there's some ambiguity there or whatever. Well, these dudes put the light source and detector in an actual inertial frame. They put them in the lab frame. And we know that the laws of physics always apply in the lab frame. And then we know that they make the correct prediction for everything. So these two are definitely in an inertial frame and as defined by any theory, known to physics. So they should definitely not measure a fringe pattern proportional to any sort of rotation, because they're in inertial frames, right? And the speed of light should reach them at a constant speed. So here we're looking at just another view of that configuration there. They also did a configuration where they had a detector on the rim of the device as well. So part of the beam would off split to a detector on the rim, and then the rest of it would go back to the source. And then there was also the detector fixed to the lab wall too, where they would compare the measurements to see if the rotating frame matched the lab frame. And what do you know, lads? They made the correct prediction using the classical derivation for the Sagnac effect. And the general relativity theory makes the wrong prediction and has to invoke a fictitious frame. So we'll take a look here at this picture, which is really the only one I could find of their experiment. And it's pretty bad. You can't really tell what's going on here, but behind us here in the dark somewhere, we have the lab wall, and we have the source and the detector. We have our mirrors up here, and then we have our rotating platform underneath with the 45-degree angled mirrors to send it back to the lab wall. And then on the side here on the rim is a detector for that configuration. So that's what the apparatus looked like. So it's spun here under a rotor, and then it's fixed up here to the top into the ground. So, all right. So when we get into the end of the paper here that they published, we have the prediction for the classic theory. We make the correct prediction for the fringe displacement, and the relativistic prediction is off by 10 times smaller. And that's without using a fictitious frame. And when they use the fictitious frame, they make the correct prediction, but that's, they're not supposed to do that. And then we have, so if that's not bad enough for those lads, we have 2004, Ruyong Wang and others use a fiber optic gyro in a parallelogram configuration and show that only the portion defined here up at the top that's covered in green measures motion relative to itself. And then here we're looking at the graph for the line. Look, the more the velocity increases, the more fringes the increase, directly proportional, one would say. So he's showing a direct measurement of linear velocity, and the only way that you could make this measurement is if you preserve the distance here with respect to absolute space. So I have a section in red here on the corner and another section in red where the parallelogram ends. So if you're moving from side to side there, you have to preserve that distance in absolute space and then assign imaginary velocity vectors for the electromagnetic process to traverse at different timings based off of that velocity. And that's the only way the measurement could be made, and that is directly antithetical to relativity theory. So here we have, we're going to read a little bit from the paper here. Therefore, it is confirmed that the contribution to the phase difference a light-moving waveguide is independent of the refractive index of the waveguide and independent of the loop configurations. To study the relationship between the motion of the fiber and the fiber orientation, we conducted an experiment in which the fiber zigzags and has an angle theta with respect to the direction of the fiber motion. Thus, the fiber segment has an actual length of delta L. Its effective length is delta L cosine theta, which is a projection of the fiber onto the motion direction. As shown in figure 2, our experiment demonstrates that the effective length contributes to the phase difference, not the actual length. Therefore, the phase difference is delta phi and not 4 pi nu delta L over C lambda. But let's see. But is the equation 4 pi nu delta L cosine theta over C lambda equals 4 pi nu times the dot product of delta L over C lambda, which is the dot product between the two vectors. The further experiment was conducted to study the phase difference between the different segments of the loop moved at different speeds. Figure A3 shows the optical parallelogram where the two arms move the conveyor and the bottom arm is stationary, or move with the conveyor. While moving, the two side arms are flexible, kept in the same shape so that the phase difference in these arms cancel each other out. There is no phase difference in the bottom stationary arm. Therefore, the detected phase difference is contributed solely to the motion of the top arm. So if you get into a conversation with a relativist and they start saying, well, yeah, the device it made the measurement with respect to itself, like, that's explicitly against the rules and regulations of relativity theory. So earlier we talked about the explanation for relativity and how they tried to explain this. So we'll get into a couple explanations that they give for the Sagnac effect, which is a first order measurement of velocity and which outweighs the second order effects of link contraction and time dilation. So they get into a situation where they have to invoke a fictitious frame, a cylindrical coordinate system noted here. And then if you were to look at that on a graph, this is what it would look like. You would have a stationary observer here denoted by this line. He would be experiencing no deviation in time or space. And then you would have your moving observer here. And then the deviation from these two would be based on this guy's velocity at the outer rim of the apparatus. So this is how they're accounting for that change in distance and keeping the timing with respect to the stationary observer here at this fictitious frame that they've invoked to account for that timing offset. Now, that was from Tartaglia 2015, and they were explicitly trying to explain Ruyong Wang's experiment where they invoke an arbitrary midpoint, like I showed in the over here, where I have these 2 points in absolute space starting and ending. They took the position of this midpoint here. So if you imagine this red circle would be just a midpoint, that's what they invoke for their transformation, which is, again, explicitly against relativity theory because then they have to assign imaginary vectors for electromagnetic processes, and that's, superfluous in Einstein's theory. So anyway, it can't be explained without doing that. And then at the end of the derivation here for Tartaglia and the boys, they throw in the gamma factor, which is crazy because link contraction and time dilation are a function of the square of the velocity squared over c squared. So it would be much too small. Actually, I think I said that wrong. It's a function of the velocity squared over c squared. There we go. And it predicts a much, much smaller fringe that would be, it's just not even on the table what they do there. So it's a term that would cancel out in the final formalism, and they're just left with invoking a fictitious frame. So here we have 2002, Berida and the boys get together and try to explain it as well. And they invoke the old fictitious midpoint with respect to, absolute space. And they're not able to explain the physical measurement either because their theory predicts no fringe and or a much smaller fringe, and we're looking at a full-grown baby fringe here, fresh out of wherever babies come from. So to wrap up here, we have another attempt in 2024 from your boy Lambar, And this guy's like, listen, guys, we're not going to invoke special relativity. That's flat space time. Flat space time has no ability to explain rotation. That's crazy talk. What we need to do is grab a curve metric tensor from curve space time from the general theory. We need to take differentials from it, from each XYZ coordinate, and make infinitesimal flat space time from that. Definitely not the same as flat space time, but very not dissimilar. You know what I'm saying? Wink, wink. And then we'll hit up a cylindrical coordinate system from there, and we'll have our fictitious observer, and we'll preserve distance, take into account for the timing offset. And then we'll conclude that the phase difference is due to relativity of simultaneity, which is basically stating that the relative motion as if you can imagine like little photons hitting the beam splitter as the motion is going on, each individual split would be, a simultaneous event happening at two different times with respect to the moving observer, which would be the light source. And then the recorder would be, dude, it gets preposterous out there. But anyway, he's breaking it down to like infinitesimal relative simultaneity events, but invoking an absolute frame to even begin to declare that, which is antithetical to relativity of simultaneity, because it would show that there's an absolute time and space, and you wouldn't be able to have relativity of simultaneity with respect to absolute time and space. They're antithetical. So conclusions: Sagnac falsified special relativity and general relativity. Wang double extra falsified special and general relativity. Any interferometer. That's it's a falsification squared, some would say.
It's a superlative of the falsification. It got super dope right there.
Yes. So any interferometer configuration is valid. It doesn't matter if it's at a single right angle to itself or if it's at a closed loop circuit. The single right angle will just have less sensitivity towards the measurement because it has less infinitesimal points to be of contact with the velocity vector. Let's see. All interferometer measurements are first order with respect to absolute time and space. All motion is relative to absolute time and space, as predicted by the alpha model presented by Bennett. Shout out to our boy Cassander presenting the alpha model, which is the absolute lab frame and flexible ether theory. Those are the acronyms when you break it down. So the Earth is stationary with respect to a dynamic ether. And that is the TLDR on Sagnac. Hope you guys enjoyed. If there's any questions, I'm available.
Well, did you cover how they immediately said that it's a rotational effect, not to worry, and none of this matters or whatever? Was that or did they do more than that?
Nope. They still say that.
So that's just so all this being said and all this being true, they just go, nah, it's rotating.
Yeah.
That's
What's interesting, if you pull out an inertial navigation system manual, like a modern one, even though most people will say the special relativity doesn't apply to a rotating frame, very erroneously, when you open up that manual, they'll show you. Actually, I think I have a diagram of it. Give me 1 second. They
say it doesn't apply to rotating because of this?
No. They use special relativity and they invoke a fictitious frame at the center, and they just don't even talk about how that's supposed to be the general relativity explanation. They treat it as SR under the same thing without using a flat spacetime metric. So yeah, inertial navigation system. Here we go. We'll take a look here at their explanation right here. All right. So this is a diagram. Oh man, it's not very big. Let me see if I have another one. Nope, unlucky. We'll have to deal with the DS one. But if you'll see here, they just drew circles and then they have an observer at the center here. And then he's measuring a timing difference with respect to the moving observer. So the same way that the boys here, Tartaglia did it with their graph. They do the exact same thing. They just invoke a fictitious frame at the center. Yeah, and
I guess I was
they
trying to get ammo to like defeat the argument that it's not a rotating frame, because when I first presented this, I got met with a whole room full of like straight nuh-uh, and I was like,
oh yeah. No, it
I
doesn't.
don't know.
Yeah. It explicitly replies to a rotating frame regardless, right? Because of what Einstein said in his 1905 paper here, where he talks about his equations hold good in any closed polygonal line, and in any continuously curved line. So if any closed loop circuit, his equations apply. So if you have an interferometer, yeah, you're good. And then also that's how they explain Thomas precession with Lorentz rotations.
What is Thomas precession?
Thomas precession is the anomalous orbit of an electron, and they say that that's happening due to link contraction and time dilation. And the way the way that they put link contraction and time dilation into a rotating frame is you can just like do an integral, and take infinitesimal sections of time. So you can just define any arbitrary section, and then any elapsed amount of time is going to be, that electron is going to be in a different position. But it's also its coordinate system is going to be offset by a theta angle relative to the, first measurement that you took, or, for your arbitrary defined time or whatever. So basically, if you take that theta angle, you can offset the new position to make them both orthogonal, and then you can do your Lorentz transformation. So if you do that twice, 2 rotations is equivalent to 1 Lorentz boost. So they do that, and they've dude, I know, right? So they've canonized rotating frames in special relativity anyway. So like nobody can claim otherwise.
I didn't know. Is Lorentz boost a real thing?
Yeah, so a Lorentz boost is your classic link contraction time dilation. In a Lorentz rotation,
Okay.
2 of those is equivalent to 1 link contraction time dilation.
Jeez.
So now that we're all caught up on the established lore and literature or whatever, they can't claim that. And then even if they do, right? So if they'll be like, okay, well, my general relativity, it's like, okay, what does my general relativity predict? Does it predict that there will be a first order timing difference, or does it predict link contraction and time dilation as a function of the, velocity, the same way that it would for the special theory? So it doesn't do them.
The people
It doesn't
who put that forward don't know what it predicts.
No, they never do. It's preposterous. That's why they don't even try to get into the details in the inertial navigation system manual. They're just like, look, boys, here's a circle. Here's a fictitious frame. Here's a timeline of distance. Here's how the moving observer has a different distance. And this accounts for the timing offset for the speed of light.
Here's
Everyone
why
happy?
Sagnac doesn't matter. Yeah, right.
Yeah. And then they go on to use the, what's it called? The classic equation. They're like, you don't even have to Lorentz transform, boys. You're good. So,
Craziness.
I bet when they go Galilean, they feel naked.
Yes. Yes. All right. Let me check the chats here, see if anyone has any questions from the YouTubes before we wrap it up. All right, it looks pretty clean, lads. I think we made a nice 44-minuter. Little Sagnac recap.
Were you going to call it a clean getaway?
Yep. All right. See you guys on Thursday for Research and Reading Night. We're going to be reading a little Edward Daddy Jr., a book that Eric presented. I forget the title of it right now, but I'll have it posted at the end of this here. So we're going to read a little bit from that, see how that goes. And then Friday will be Flat Earth Fridays, episode 119. And then Saturday, I'll be hanging out with Jaron at 3 p.m. Eastern, 12 p.m. Pacific. So if you're a subscriber to his or whatever, the VIP hangout thing, I'll be on that. And then Shane will be doing a presentation for the Czech lads, an international presentation, if you will, on Saturday at 9 p.m. Eastern. I think that is, Shane.
8?
It might be 8 or 9. So stay tuned for that.
One of those definitely valid. That should be fun.
Awesome. All right. Peace.